Good day, grade 12 learners. Welcome to today's maths revision lesson. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, today we are looking into revising some grade 12 concepts as well as grade 11 concepts that would be essential for you when you write your paper tomorrow. Because of time, we won't be able to do all the topics. So our focus topics would be differential calculus as well as functions, since you would see that these topics make up bulk of the marks in paper 1. They make up more than 40% of paper 1. Right, let us first look at the mark distribution. Now you can see that algebra, it's 25 with a variance of 3, which means that it can range between 22 and 28 marks. Sequence and series as well. Functions, it ranges between 32 and 38 marks in an exam paper. Functions would 32 to 38. Finance, 12 to 18. Differential calculus, it's 32 to 38. Probability, it's 12 to 18. Now, if you look at differential calculus as well as functions, you can see that both these topics combined, they'll make up more than 70 marks. They'll make up more than 70 marks. That is why today's revision session would be centered around those two topics. Right, what is also important and crucial at this juncture is for you to have your own targets, and you need to then work upon those targets. You should set targets per topic. Right, for you to get a minimum pass, you can set up a target of 15 in algebra, that is question 1. You can set up a target of 12 in patterns. You can set up a target of 15 in functions and so on. If you set those targets and when you do your revision and when you practice for the paper, after writing questions on algebra, then after marking for yourself, you check whether you are able to meet the target that you've set. Now, for you to get a minimum pass, if you add all these marks, you'd see that it would be 67 marks minimum, but you only need 45 marks to pass the paper. Right, if you are gunning for a bachelor pass, your targets can be as follows. For algebra, it's 18. For patterns and sequence, it's 15, and so on. Now, if you check, you only need 75 marks for you to get that bachelor pass. Remember, you'd get it in conjunction with other subjects. You don't just get these marks only in maths, then with other subjects as well, then you are going to get your bachelor if you ensure that you get a minimum of 75 marks per paper in mathematics. Right, let's look at the weightings according to those cognitive levels. Remember, the questions that they ask in exam papers would range up across 4 cognitive domains. So if you check here for knowledge questions, the questions that would want you to recall, questions that would want you to identify formula, use algorithms, estimate, and round off, that would only make up 20% of the paper, which is about 30 marks. Those are generally simple questions. Right, moving on to the second part, you see that it's routine procedures. Yeah, when you are required to prove theorems and derivation of formula, this you can see usually in paper 1, it is tested when you want to prove the sum of n terms of either a geometric or an arithmetic sequence. That would just be a proof, so it falls under routine procedures. You perform well-known procedures, that is also routine. Simple applications, a derivation from given information, identification and use of a formula, but now you change the subject of the formula, then it falls under routine procedures, and that would make up 35% of the paper, which would range between 52 and 53 marks. If you check between 52 and 53 marks together with the 30 marks from knowledge questions, this forms about 82 marks, approximately 82 marks. This 82 marks is only for knowledge and routine procedures. These are questions that are considered to be generally simpler. Right, and then you have your complex procedures. This is a level 3 question. Here we are looking at questions where there is no obvious route to the solution. We are dealing with problems that might include real-world contexts, problems that require conceptual understanding. They will make up about 30% of the paper. And then we look at problem solving. These are higher order questions. These two refer to higher order questions. With problem solving, you need questions that are necessary, non-routine. You need questions that are unfamiliar. If you look at past papers, you see questions that are different from the norm of past papers. Questions that might require you to break a problem down into its pieces. It might require extrapolation and interpolation and so on. These are higher order questions. They would make up of only 15% of the paper. Now, with this being said, you can see that from level 1 and level 2 questions, you can get a good mathematics pass. You can get your bachelor pass by just doing well in level 1 and level 2 type questions. What is also important with you and target setting is that when you start writing, they'll give you about 10 minutes reading time. Please use the 10 minutes reading time to target specific questions that you then go and answer first before you attempt others, because in most cases you spend a lot of time on questions that are a bit difficult, only to find out that you'd have answered other questions and you don't get enough time to do so. So you set your targets and then you make sure that you use the 10-minute reading time to target specific questions that you can answer. Right. Our session will then start with functions and inverses. You would recall functions start from grade 10. Do them in grade 10 with only vertical movement, and then in grade 11 you start to look at functions that will also involve horizontal movement, and then in grade 12 you then look at the inverse functions. Now we are going to be looking at the functions that you need to know for you to pass, or for you to get good marks in the prelim paper that you're going to write tomorrow. Right, these are the examined concepts. We should understand how to sketch all the functions as well as their inverses. Usually to sketch functions, we use the dual intercept method, and then we use the parameters to understand the shape and all the other things. Now we also need to know how to determine the domain and the range of each function, and we should also know how to interpret all functions together with their inverses. Right. Let us zoom into the linear function and look at some of the parameters that the linear function would have. Obviously we look at the standard shape. The linear function would always have the gradient. M or A here represents that gradient, and we know for us to calculate the gradient we can use change in y over change in x, y2 minus y1 over x2 minus x1. That is how we can find the gradient of this linear function. Right, we see that here the gradient, or the nature of the gradient, determines the shape. You see, if m is positive, then we have that this is an increasing function, and then here there's an error here. If m is negative, then you see that there's a decreasing function. Now we also define domain and the range. The domain, we say those are the x values, all the permissible x values for which the function is defined. And for a straight line, the domain is from minus infinity to infinity. It takes all real numbers, and then the range will also take all real numbers. That is for a linear function. A linear function does not have a turning point, a linear function does not have an asymptote, and a linear function does not have an axis of symmetry. Right, moving right along. Now we look at the rectangular hyperbola, or the reciprocal function. We know the standard form is y is equals to a over x minus p plus q. Now we are looking at the parameters p and q that represent horizontal shift as well as vertical shift, movement on the left and the right, and as well as movement up and down. Right, we see that if a is greater than 0, because a gives us the shape, we get that it's a decreasing function. So those arms of the parabola, or the hyperbola I should say, should be on the second and the fourth quadrant, or rather the first and the third quadrant. It should be in quadrant 1 and also in quadrant 3. When a is less than 0, that is an increasing function, and then the terminal arm there should be on the second quadrant as well as the fourth quadrant. Right, they are speaking of increasing and decreasing function. You also saw here in straight lines, I said if m is greater than 0, we are talking of an increasing function. Here we are talking of a decreasing function. Now one might ask, what is an increasing or what is a decreasing function? In mathematical terms, we define an increasing function as a function where x increases, y also increases. If you check that from left to right, the values of x are increasing as well as the values of y are also increasing. Usually I would use a toy car approach to try and understand the concept of increasing and decreasing function. If you are to place that toy car on this particular slope and you move it up, as it moves up, we say that because it's moving upwards now, the graph, if this was the graph increases. But if you are to place that particular toy car and you push it downhill, as it moves downhill, we say that the graph decreases. Now if you check with these hyperbolas, and you investigate, say you investigate the terminal arms, or rather the arms of that hyperbola, and then you want to know whether it's an increasing or a decreasing function, you are going to investigate that from left to right. We always read, just like when you read a book, you'll always read from left to right. Also in mathematics, when we deal with functions, we always read them from left to right if we are looking for the values of x, and then we read them from bottom to top if you are looking for the values of y. Now if you are to place your toy car here, moving it from left to right, you'd see here that it would be moving downhill. So we say that it's a decreasing function. This terminal arm here would be a decreasing function. And if you are to place it here as well, you see that it's also moving downhill. So you say that it's a decreasing function. So this particular hyperbola that is in the first and the third quadrant is represented by what we call a decreasing function. But now if you are to check the other one now, if you are to check the one that has rays on there, second and fourth quadrant, if you are to move your toy car here, you see that it would be going up. Also here, if you are to place it there, you see that it's also going up. So we say that it's an increasing function. Right, when we look at the domain of a hyperbolic function, it takes all real numbers except the asymptote, because the asymptote is where the graph is not defined, as well as the range. When we move on to the range, it also takes all real numbers except for the asymptote as well, because the asymptote is where the graph is not defined. So the graph is defined from minus infinity to infinity except for the asymptotes, that is the domain. The range is also defined from minus infinity to infinity, excluding the asymptote. So we say that this graph has no turning point. The asymptote x is equals to p, you get it from the equation x minus p is equals to 0. So x becomes p. That would be your vertical asymptote. Horizontal asymptote, you take it exactly as it is here together with its sign from the equation. So you see that the graph would be moving up and down. The value of q there represents the asymptotes. If you want the axis of symmetry, this is an equation you can use to get the positive one, and this is an equation you can use to get the negative one. All right, moving right along, we are now looking at the second degree function, the parabola, or what we normally refer to as the quadratic function. Now you see that there are two standard forms here. There's a center form, and then there's also this one with ax squared plus bx plus c. So it has two standard forms. Now obviously both the standard forms would have the value of a, which give us the shape. If a is positive, it's a smiling face parabola. If a is negative, it's a sad shape parabola. Right, with the domain, the parabola is defined from minus infinity to infinity, so it's x an element of all real numbers, but the range now depends on the value of the turning point. If you check here, I used f of minus b over 2a. That is the x value of the turning point, here represented by q, here represented by q as well. Now if you check the range, if you have your parabola this way, suppose that this is your parabola, this value here can be written in the form of p and q. Both of them are positive, but also if you use the other form, p is the same as the x value of the turning point. It's minus b over 2a. That is to get the x value. How do you get the y value? You always substitute x where you see, or you substitute minus b over 2a where you see x. So that is the y value, because you would be substituting the values of x that you obtained in the original equation to get the corresponding value of y. Now if you check this hyperbola here, because of the turning point, the range here would be y will take all real numbers, but y should be less than, it should be less than or equals to q, because the graph is defined from negative infinity up until the turning point. Right, the turning point, we get it from by using minus b over 2a. You know that also we can use differentiation to get the turning point, because that's the maximum point or the minimum point. We can also use x at the turning point is equals to, if you have the x-intercepts of that graph, you can find the average of those x-intercepts. You add the two and you divide them by 2, or you find what you call the midpoint. So the midpoint of the x-intercept will also give you the axis of symmetry, which is the x value of the turning point, just like it's indicated here. The axis of symmetry is minus b over 2a in the first form, or if you are given the turning point form, then you can use x is equals to p. Right, moving right along, we are now dealing with an exponential function. And now dealing with an exponential function of this form, y is equals to a b into, or a times b raise x minus p plus q. So it has both horizontal and vertical movement. So the shape here, the shape of the exponential function, if you have y is equals to a times b to the x minus p plus q. The shape of this would depend on both the values of a and the values of b. But first, there are rules that we learn in grade 10 when drawing exponential function. The most important rule here would be the exponent should always be positive. The exponent should always be positive. That is how you're going to see whether it's a fraction or it's just a whole number. The exponent of the variable x, the exponent of x, or rather the coefficient of x should always be positive. Let's say for an example, you have y is equals to 2 to the minus x. You see that this exponent here is negative. So it should always be positive. So what we can do is we can write this as 2 to the minus 1 times x. Now this exponent is positive, but 2 to the minus 1 is half. So this would be half raised x. So now you can see that this is a fraction there. You can see that this is a fraction. So that is very, very important. And then now, what does this parameter, or what do these parameters tell you? The value of p, remember, it represents the horizontal movement, and the value of q represents the vertical movement. Now, how do we then get the shape? B tells you, if you look at an exponential function, any exponential function for argument's sake, any exponential function here, can draw any two like this. If you check, when you draw them, you start closer to the x-axis. It's either you'd start on the negative x-axis or you start on the positive x-axis. So the value of b tells you where to start. It tells you whether you start on the positive x-axis or you start on the negative x-axis. If b is greater than 1, b is greater than 1, then you start on the negative x-axis. But if b is a fraction, then you're going to start on the positive x-axis. That is basically what the value of b tells you. Remember, b cannot be 0. It can also not be equals to 1. It should be a number superior than 1, or it should be a fraction. Right. Now, when we look at the value of a, the value of a works with the value of b as well. The value of a tells you whether you start above or below the asymptote. If a is greater than 0, it tells you you start above the asymptote. But if a is less than 0, you start below the asymptote. So it tells you whether you start above or below the asymptote. But it also tells you whether you face up or you face down. So if you start above the asymptote, you face up. If you start below the asymptote, you face down. That is the value of a. Right. Like for an example, if you check the shapes, if you take the shape and position here, if you check this first graph here, if you check this first graph, a is positive, it's above the asymptote. If you check the second graph as well, a is positive, it's also above the asymptote. If you check the second one, or rather the third graph, a is negative, it's below the asymptote. The last one, a is negative, is also below the asymptote and facing down. Now, if you check b, let's check b. B is greater than 1. I said to you, if it's greater than 1, you start from the negative x-axis. If you check, this graph started from the negative x-axis and faces up, but because b here is a fraction, it starts on the negative x-axis. Similarly, you can do the same with the last two graphs. Right, domain and range. Domain takes all real numbers for an exponential function, but the range of an exponential function is such that y should always be greater than, it should be greater than the horizontal asymptote. It should be greater than the value of q, because the graph is defined above the value of q, or it should be less than the value of q when you have the value of a being negative. The asymptote, it only has a horizontal asymptote, there is no vertical asymptote, and there is also no axis of symmetry. Right, that is the summary of those particular functions that we're going to deal with. We call them the algebraic functions. Right, now let us look at an example. Let us look at an example on these functions. Our examples start with a rectangular hyperbola or a hyperbolic function. Now, if you look at the question here, it says the function f of x is x minus d, x minus p is sketched alongside where p plus q are constants. The dotted lines are the asymptotes. B2 is to 2 maps 0 is a point on F. The asymptote intersected P. Now, if you check this form that they gave you, it's not a standard form. It's not a standard form. It's given as y is equals to x minus d over x minus p. This is non-standard. This is non-standard. Remember, sometimes they can also represent it this way. Sometimes they can write y x minus 1 is equals to x minus 2, for argument's sake. This is still a hyperbola. It's still a hyperbola. It's just that it's written in non-standard form. You should be able to write y as the subject of the equation and write it in standard form. Now, if you check here, this one, they want us to find the values of d and p. The values of d and p. We see that from this denominator, we have that x minus p is equals to 0, x is equals to p. That should give us our vertical asymptote. It should give us our vertical asymptote. And fortunately, in the graph, it's given as minus 1. So you see here, x is minus 1. So our value of p is minus 1. So already we have the value of p, and then now we're looking for the value of d. Now, if you are to look at the function itself, f of x, let's substitute the value of p, x minus d over x minus 1, which would be x plus 1, if we substitute the value of p. Now, we are given a point B on the graph. A point B on the graph where x is 2 and y is 0. So we can substitute that point. So we'll get that f of x would be equals to, right, our f of x is y is 0, and then x is 2. This is 2 minus d over 2 plus 1. Now, if you are to add 2 plus 1, you get 3, and you multiply both sides by the LCD, you get that 2, you get that this would be 0 is equals to 2 minus d, and then d becomes 2. D becomes 2. So you have the value of p is minus 1, and the value of d is minus 2. Right, moving on. Show that the equation can be written in that form. Now, if you check, we've worked out the value of d. So we have that this is x minus 2 over x plus 1. This is not in standard form, but they want us to write it in standard form. So you can do this using 2 or 3 different methods. I'll just show you 1 or 2 now, so that you can be able to know what to do. Right, we are having our f of x is equals to x minus 2 over x plus 1. If we want this to look that way, it means we should have 2 fractions. So we should try to make our denominator, in this case, we should try to make our numerator to be the same as the denominator. So what I can basically do is I can, on the numerator, add 1 and subtract 1. If you check, if you add 1 and subtract 1 on the numerator, you get 0. 1 minus 1 is 0. So it's the same as x minus 2. Now, because this part looks the same as that, that is the idea that I wanted to have here. Now, which means that I can then say this is x plus 1, and then I add these two, minus 1 minus 2, subtract them, I get minus 3 over x plus 1. Now, if I have this as y is equals to a minus b over c, I have that c is a common denominator, so I can divide both terms by that denominator. So I can divide x plus 1 by x plus 1, I'll get 1. And then I can divide negative 3 with x plus 1, I get minus 3 over x plus 1. So this simplifies to minus 3 over x plus 1 plus 1. So that is how I will then change this and write it in standard form. Alternatively, I can use long division. This is the one that I like most because it works for all these hyperbolic functions. It's a general approach that one can use and is not that difficult. Right, I'll give you an example. Suppose that you have 7 divided by 2 and you want to divide that using long division. What we can basically do here is we have that 7 is the dividend. It's what is divided. And 2 is the divisor. Ask yourself, how many times does 2 go into 7? It goes into 7 3 times. Goes into 7 3 times. You write that at the top there as a quotient. Then you multiply your quotient with your divisor. Here you get 6. When you subtract the 2, you're going to get 1. You're going to get 1. Which means that now I can express the fraction 7 over 2 as, I can express the function 7 over 2 as 1, the remainder, this here we call the remainder, as the remainder divide by the quotient, or rather divide by the divisor plus the quotient. So if you check, 7 over 2 can be written as a partial fractions, half plus 3. Can be written as 2 separate fractions, half plus 3. If you take half plus 3, that's 3.5. 7 over 2 is also 3.5. So you have that now. You've written 7 over 2 as 2 fractions. So that's how useful long division would be here. So we adopted the same approach here. We say if we have x, f of x is x minus 2 over x plus 1. This can be written in long division this way. What I'm dividing is x minus 2. What am I dividing it by? I'm dividing it by x minus 1. If I do so, I'll check how many times does x go into x. Goes into x 1 time, or x divided by x is 1. Write that as the quotient, and then you multiply. You get that this is x, you get that this is minus 1. Now, if you subtract the 2x minus x here, you get 0. And then you're going to get here, let's see the divisor here. I made a mistake. The divisor is x plus 1. I'm dividing x minus 2 by x plus 1. So this becomes x plus 1 here. So you get that minus 2 minus 1, you get minus 3. So we see that x minus 2 over x plus 1 can be written as the remainder divided by the divisor plus the quotient. So this would be minus 3 over x plus 1, and then that would be plus 1. So we know that this x minus 2 over x plus 1 is the same as our f of x. So our f of x is minus 3 over x plus 1, plus 1. So that is how you can change the form of that using the long division approach. Right, moving right along, they say write down the coordinates of P. Write down the coordinates of P. Remember, we have the equation already. Our equation is given by y is equals to minus 3 over x plus 1 and then plus 1. That is our standard form of the equation. Now, if we want the coordinates of P, we know that P here is the point of intersection of our asymptote. So we have that the value of P is minus 1 and the value of Q is 1. So that would be our point of intersection P, the point of intersection of the asymptotes. So they ask now, is f an increasing or a decreasing function? I think we spoke about that. You're going to read the graph from left to right. Now, if you check here, if I can put my toy car here, as it moves here, it would be moving up. And if I place it here on the extreme left, as it moves here, it would be moving up. So if my locomotive or my toy car moves up, we say that the graph is increasing because it moves up. The value of x is increasing. When x increases, I mean y also increases. So this should be an increasing function. It is an increasing function. Now they say write down the values of x for which the function increases. Now this function increases. Remember, it's not defined on this line. The function is not defined on that line. So it increases from minus infinity until where it's not defined, that is minus 1. It also increases just after the line where it's not defined, that would be 1 to positive infinity. That is one way of writing the values of x for which it increases. That is if you look at the graph from left to right and you are using what we call the interval notation. Now you can also use another notation. X is an element of all real numbers. We accommodate all real numbers except minus 1. That is when this graph increases. Or we can also use another notation and say it increases when x is less than minus 1 or when x is greater than minus 1. That is if you use the inequality notation. Right, those are the values of x for which the graph increases and decreases. We move right along. They say write down the domain. Write down the domain. Let me check something here. Okay, write down the domain of G. Right, if you check here now, we have a new function G. We want to write down the domain of G if g of x is given by f of x minus 2. This is a transformation. Obviously, in functions, you also need to know and understand your transformations. So there are two ways of doing this. First one would be you can look at the graph. You can look at the original equation, and from the original equation, write down the domain of the original function and then use the transformation that is given to write down the domain of the new function. Or you can use the transformation directly on the equation and write down the domain after forming a new equation for G. So let us look at the graph of f. The graph of f is given by f of x is equals to, this is minus 3 over x plus 1 plus 1. That is our graph of f. Now what we want to do here is to write down the domain. We know for the domain of f, what would be the domain? The domain would be x, an element of all real numbers, but x cannot be that particular vertical asymptote. X cannot be -1. That is the domain of f. Now, what is the transformation? Let's look at movement from F to G. What is the transformation? Where we see x, we put x minus 2. So the transformation is x minus 2 is equals to 0, x is equals to 2. That is the movement. So the graph of G is obtained after moving the graph of F by 2 units to the right, by 2 units to the right. So what we can basically do is we move all the points from F, we move them by 2 units to get to the graph of G. So for G, what would be the domain? The domain would be x, an element of all real numbers, but we move all the x values by 2 units. So we're going to obtain that this is x is not equals to positive 1. So that's our domain, x, an element of all real numbers, but x cannot be equals to 1. That is the domain of G, where because G is a graph that has been transformed by moving the graph of F by 2 units. Right, now moving on to the second method that we can basically use here. We can find the equation of G. How do we find the equation of G? We see here that G of x is f of x minus 2. So when we see x in the original function, we put x minus 2. Obviously, the original function is this one, minus 3 over. Where we see x, we put x minus 2. And then we have that this was plus 1. Plus 1. You can see here where there was x, I replaced that with x minus 2. So our f of x in this case would be minus 3 over x plus 1. Oh no, this is our G of x now. This is our G of x. Sorry about that. This is our G of x. So our G of x would be minus 3 over x plus 1 and then plus 1. So what would be the domain of G? X, an element of all real numbers, but x cannot be the asymptotes. X cannot be equals to, no, minus 2. Sorry, I made an error here. Minus 2. If I add minus 2 and 1, I'll get that this is x minus 1. So x, an element of all real numbers, but x cannot be equals to 1. Sorry about that slight error that I made there. Right, that's how you can write down the domain of G. Right, we are done with the hyperbolic function. We quickly move to the parabola or the second degree function. If you check here, the parabola is drawn and the straight line as well. They are drawn on the same set of axes, and they want us to then determine the coordinates of C, the turning point of F. We are given the equation of F and we want to determine the coordinates of C. Sorry, the coordinates of C, which is the turning point of F. Now, to do that, we know we can either complete a square, we can use axis of symmetry minus b over 2a, or we can use calculus. Now, if we use x is minus b over 2a here, we know that our value of b is minus 2 over the value of a is minus 1. So x would be equals to, if you look at this, x would be equals to minus 2, which is 2 over minus 2. That should give us minus 1. So that is the value of the axis of symmetry. And we know for us to get the y value, we're going to substitute minus 1 on the original equation. So f of minus 1 is minus into minus 1 squared minus 2 into minus 1 plus 3. Now, if you add all that, then you're going to get that this is 4. Because minus into minus 1 squared, that would be minus 1 plus 2 plus 3 is 5. So minus 1 plus 5, it gives us 4. So f of minus 1 is equals to 4, which means the coordinates of C would then be minus 1 for x and 4 for y. So that would be the coordinates of the turning point. Obviously, you can also make use of a calculus there, or also completion of the square. Right, moving right along, determine the coordinates of A and B. If you check on this graph, A is a point of intersection for F and G, but also A is a common x-intercept between F and G, or of F and G, and B is the x-intercept. So if we want to find the coordinates of A and B, we say A and B are x-intercepts. A and B are x-intercepts, and we know to find the x-intercepts we put y to be equals to 0. So if we want to find these x-intercepts, for x-intercept y is equals to 0. If we equate y to 0, we're going to get 0 is equals to minus x squared minus 2x plus 3. Dividing by negative, uniformly we get x squared plus 2x minus 3 is equals to 0. If you find the factors here, remember, if you can't work the factors out, you can always make use of the quadratic formula. So here, if we use inspection, we see that the factors of 3 is 3 and 1. Then the bigger one should be positive because the middle term is positive. So x is equals to 1, or x is equals to minus 3. Minus 3 obviously is on the negative x-axis where A is located, and 1 is where B is located. So if we want to find the coordinates, then the coordinates of B would be 1 is to 0, and the coordinates of A would be minus 3 is to 0. So those are our values of A and values of B. Now we are looking for the values of M and C. Now let us check what we have on this. We have the coordinates of A, 1 and 0. The coordinates of B, minus 3 and 0. We have the coordinates of C, minus 1 and 4. Now we are looking for the values of M and C as defined in G. You can see that the value of M is the gradient of the straight line, and C is that constant. Now how do we find the gradient of a straight line? We can use M is equals to y2 minus y1 over x2 minus x1. We can take it from point A and point C because both point A and point C, they lie on the straight line. So if we take y2 minus y1, that would be 4 minus 0 over minus 1 minus 1. So the value of M here should be, if you check here, 4 minus 0 over minus 1 minus, let me change this here, x2 is 4, y2 minus y1, 4 minus 0, this is y2 and this is y1, 4 minus 0 over, I have minus 1, x2 here and x1 here, minus 1 minus 1 here. That's what I'll basically have here. That's what I'll basically have. y2 minus y1 over x2 minus x1. So we get that this is negative 2. Right. No, I'm making a mistake here. There's an error here. The coordinates of A, let's check. We said the coordinates of A are minus 3 and 0. Right. It's just a small mistake here. Allow me to fix it here. The coordinates of A are not these ones. The coordinates of A are minus 3 and 0. And the coordinates of C are minus 1 and 4. So those are the coordinates of A and C. So the gradient here would be y2, which is 4 minus 0 over minus 1 minus 3 in this case. So this would give us a gradient of 2 because this gradient should be positive. So I made an error there and used coordinates of B instead of coordinates of A. Now we already have the value of M. We want the value of C. We can use y is equals to mx plus c, and we can substitute any point on the graph. can substitute any point on the graph. I can use a point that is on the graph. I can use a point point A, which is -3 and 0. So I will substitute y at A is 0 is equals to the gradient, which is 2, C, our x is -3 plus C. So we find that now C becomes +6. So we've worked out M is 2 and C is +6. So that is basically what we're going to do there. Right, moving on. Calculate the length of CE. Calculate the length of CE and leave your answer in simplest set form. Now, we normally refer to this as the distance between the 2 points, or rather the length. You know, in mathematics, we can divide our lengths. We can divide our lengths into 3 main categories. We have a horizontal length, we have a vertical length, and we have a diagonal length. Now, when we want to work with the horizontal length, to find the horizontal length, you're always going to take your x on the right minus x on the left. To calculate your vertical length, you're going to take y top minus y bottom. That is how you work with a vertical distance. If it's a diagonal distance, then you're going to use a distance formula. If it's a diagonal distance, then you're going to use a distance formula. Now, if you check CE, CE is a diagonal distance, so we need to use the distance formula. How are we going to use our distance formula? We write down the coordinates of C, which of course we worked out as -1 and 4, and then we write down the coordinates of E, because we want the length of CE. Now, if you check point E is on the y-axis, so it's the y-intercept of the straight line. So the y-intercept of the straight line, remember the equation of the straight line, we got it as 2x plus 6. What is the y-intercept? Is when x is 0. So we have that y would be equals to 6. So this here, x is 0, y is 6. So the coordinates of E, 0 and 6. Now, if you want to find the length CE, we're going to take that. This is the square root of x2 minus x1 squared. That would be 6, or rather 0 minus 1. 0 plus 1 squared plus 6 minus 4 squared. So this will then simplify to the square root of 6 minus 4 is 2, square is 4, 0 plus 1 is 1, 1 squared is 1. So this would be the square root of 5. That would be the length of CE, the square root of 5. Right, calculate with reasons the size of ACD. Now, if you check these two questions, they will remind you of analytical geometry. So we are integrating concepts here. The concepts of paper 2 are also applied to paper 1. Integration of concept is also allowed in maths. Right, so E, they want us to find the size of ACD. They are looking for this angle here, angle ACD. So this is the angle of interest that they are looking for there. So they want us to work out that angle. Now we know from analytical geometry that we can work out the inclination of a line segment. So which is the angle that the line segment forms with the x-axis when you move in an anti-clockwise direction. So this angle here, if this angle here is our inclination theta, then it follows that the tangent of theta would be equals to the gradient of this line. I can take it as AC or AE. Now, what is the gradient of the line? The gradient of the line is 2, so the angle theta would be the arctangent of the gradient, which is 2. So if we check the arctangent of 2, From the calculator, we get that this is 63.43. So theta is 63.43. Now, if this angle here is 63.43, you can see that this triangle CDA is a right angled triangle because this angle here is 90 degrees. That is the angle that the axis of symmetry forms with the x-axis. Remember, axis of symmetry is parallel to the y-axis, so it forms a right angle with the x-axis, and this is 63.43, which means if we add all these interior angles, we're going to get 180 degrees. Therefore, we're going to have that our angle ACD would be equals to, if we add all, we're going to get 180 degrees. So it would be 180 minus 90 minus 63.43. The reason here would be sum of angles in a triangle. Therefore, our angle ACD in this case will simplify to, I take that, I put it in the calculator, I get 26.57. So that would be the angle of ACD, or the value of that angle. Now, if you check here, we've integrated concepts that are used in paper 2 with concepts that are used in paper 1, and we are permitted to do so. So you should always be prepared. Remember, we spoke of the cognitive domains when we started to say questions can be divided across 4 cognitive domains. So we are allowed to integrate those concepts. Right. Now we move on. Write down the values of x for which f decreases. They want the portion of the graph that would be a decreasing function. They want the portion of the graph that would be a decreasing function. Remember, I said with our toy car, if it goes up, we are talking about the increasing function. Now, if it goes horizontal or it stops, then we are talking about now the function has stopped. We are referring to that as a stationary point in this case. And then if it goes down, we are referring to this as the decreasing function. But you should always read the graph from left to right. Now, if we read our parabola f from left to right, you can see here, if I can place my toy car here, it will move up until point C where it stops. That is where it's not an increasing function and also not a decreasing function. Now, after C, you can see that now my toy car will be moving down. So the graph is a decreasing function there. So as it moves up there, we say it's an increasing function. So where do they want it? They want it where it decreases. So it starts from where the graph was stationary. Remember, the coordinates of C are -1 is to 4, or -1 and 4. So we see that it becomes, this graph becomes or decreases when we have that our x is greater than -1. Starting from, remember this value is -1. Starting from here, going that way, the graph decreases. Or you can also write it this way. You can also write it this way. You say it's from -1 to infinity. That's where the graph starts decreasing. That's where the graph starts decreasing. Remember, at point C, it's a stationary point. The graph is neither increasing nor decreasing. Right. The last question here, G, they say determine the values of k for which f of x is equals to k has 2 real but unequal roots. It has 2 real but unequal roots. Now, if you check here, f of x is equals to k. What happened here? If you relate that to the original function, you can see that here, where there was y, remember f of x is the same as y. Where there is y, they are putting k. Now, which means that we will be moving a horizontal line a horizontal line y is equals to k, such that we get what is intended in the question. So we move this horizontal line y is equals to k such that we meet the condition that is given in that question. Let's check the question. They say it has two real but unequal roots. It has two real but unequal roots. What does that mean? It means that our graph should have two x-intercept. 2x-intercept. Now, when we start moving this line, I'm going to redraw my quadratic here. This is my quadratic there. And this is the turning point 1, -1, and 4. And these are the x-intercepts. So we are interested in the values of y where this horizontal line touches 2 points. Now, we're going to start with where it doesn't touch any point. That's where we're going to start with our work here. So if the horizontal line is here, the graph is not, or the line y is equals to k, here is not touching any point. Now, if I move the line directly to the turning point, what do you see? The line touches the graph only once. So we say that it has one x-intercept or one root, or we say that it has equal roots. Now, check if I move it down just below the turning point, how many times does it touch? It touches the graph twice. So we say that the graph has two real but unequal roots, because this value here of x, the value of x here is not the same as the value of x there. If you continue to move the line down, you can see it touches 2 points. Continue moving it down, you can see that it touches 2 points as well. So as the line moves below the turning point, it touches 2 points and it has two real but unequal roots. So we're going to say it happens when k is just below the y value of the turning point. That is where k is less than 4, because you are looking for the values of y for which x will exhibit this behavior where it has two values. You are looking for the values of y that would allow you to have two x-intercepts. So the values of y that would allow you to have two x-intercepts start when the graph, or rather the line y is equals to k, is just below the turning point. Right, moving on here. Now, if you look at this particular question, it's an exponential function, and here we are introducing, or rather we are recalling a concept that we've worked with before. You are using parameters. Remember, we have parameters a, b, p, and q. All those parameters for each function should be understood, because they can ask you a question tomorrow on using parameters to draw a function, where they just give you the parameters and the properties of a function, and then they say sketch that particular function. Now, if you check here, we are given the exponential equation g of x is equals to a times b to the x plus q. So here we need to understand the parameters for us to be able to sketch the graph. Now, let us recall, I said to you a and b are going to give you the shape. Q is going to tell you about what? The asymptote. Is going to tell you about the horizontal asymptote. Now, let us recall what we said. We said that if b is greater than 0, then what happens to our graph? If b is greater than, no, it's greater than 1, it starts on the negative x-axis. But if b is a fraction, it starts on the positive x-axis. That is where the graph starts before it goes up or goes down. It starts just next to the positive x-axis or negative x-axis. That is B. It tells you where we're going to start. They also say it tells us about the increasing and decreasing nature of the function, but I'm not going to entertain that for now. Now, let us look at the value of A. The value of A tells us about if A is greater than 0, it tells you that you should start above Q, the asymptote Q, or above the asymptote, and then go up. That is what A tells you. Start above the asymptote, then go up. But if A is negative, it tells you to start below Q, or the asymptote, and go down. That is basically what A is telling. It tells you about the orientation. So A and B combined, they give you the general shape of the function. Now, let us look at these parameters. The parameters that they've given us, the A is negative, B is greater than 1, and Q is negative. Now, let's start with the asymptote. We generally start with asymptote in all exponential functions. The asymptote Q is less than 0. So the asymptote is below the x-axis. That is Q less than 0. That is the asymptote. Now, let's check. They say here, B is greater than 1. What does that tell you? B greater than 1 tells you you start on the negative x-axis. So the graph should be starting on the negative x-axis, either here or there. On the negative x-axis, either here or there. Now, we have that now, the value of A. What does A tell you? A tell you whether you start below or above the asymptote, and whether you go up or you go down. So now it says, because A is negative, it says start below Q and go down. Now, if we start, this is Q, we start below Q and we're going to go down. So this is our exponential function. So that is how you are going to draw that exponential curve using the properties. So this, what I've just written here, is very, very important for all grade 11 and 12 exponential functions. To get whether the function is increasing or decreasing, obviously from left to right, you're going to use your toy car. If I use my toy car here from left to right, if I move the toy car, you see that it's going downhill, which means that the exponential curve in this case would be a decreasing function. Right. Moving on, we are now entertaining the concept of inverses. We are now entertaining the concept of inverses. We are looking at the inverse functions. Remember, the inverse functions that you study at this level are these ones. Y is equals to ax plus q, or mx plus c. You also study the inverses of y is equals to a to the x. You also study the inverses of y is equals to ax squared. These are the three inverses that you're going to study. I'm going to quickly rush through them so that we can be able to answer questions on inverses and then move on to a differential calculus. Right, now the inverse of a function. How do we get the inverse of a function? Remember, there is also a concept of checking whether the inverse is a function or not a function. That is where we use the vertical line test. We're going to talk about that now. Now, if you check here, in order for us to get the inverse, we are interested in the line y is equals to x. Now, if you want to get an inverse, say you have the line y is equals to 2x plus 3. To get the inverse of this graph, you're going to interchange x and y. So x would be equals to 2y plus 3, and then you make y the subject of the equation. You get that 2y is equals to x minus 3, and then y would be equals to half of x minus 3 over 2. So this is the inverse f inverse, and this is the original function f. So we see that if we are to draw the function, the rough sketch of the function, if you get something like this, then we're going to have that it's reflected across the axis here. Now, if you look at straight lines here, you can also have something like this. Look at this one now, minus x minus 7. Look at this one now, minus x minus 7. If you want the inverse of this, you interchange x and y. So this is f of x. If you interchange x and y, you get x is equals to minus y minus 7. If you transpose y, you get that y would be equals to transpose x minus 7. So this is the inverse of x. If you check the inverse and the original function, they look the same. So some linear functions are their own inverses. So you get that the inverse as well as the original function look the same in this case. Now, remember this, they can also be terminating functions. Remember when we draw functions with arrows like that. But if we have terminating functions, where now you have open intervals or shaded intervals, then it means that particular function terminates. You need to know how to work with the terminating functions. It's not always the case that functions, linear functions, will be from minus infinity to infinity. Sometimes you can be given a linear function like this, where this point here terminates. This is 2, and this point here is minus 3. It also terminates. So if you check, the domain of this is not minus infinity to infinity. The domain now becomes x, an element of what? Minus 3 to 2. So you need to know how to work with those terminating functions. Right, let's move on to the exponential functions. Y is equals to a to the x. If for an example you have y is equals to 2 to the x, then you know, or rather you have y is equals to half to the x. These are functions. This one would be a function that starts or increases, starts on the positive x, negative x axis. It cuts that at 1 or 0 and 1. That is the y-intercept. And we have this one starting this side. It cuts at the same 0 and 1. Now, if you are to then interchange x and y in these ones, you would see that y here, or x, would be equals to 2 to the y. And in order for us to get the function, we need to change this to logarithmic form in order to make y the subject. So we can then say y would be equals to the log of x to the base of 2, because by definition the log of a number to its base is equals to an exponent. An exponent in this case is y, and then the base was 2, and then the number is x. So that's how we convert that. We can also convert this one to log form. We can have that we start by interchanging x and y. X is equals to half to the y, and then this would be the log to the base of half. X is equals to y. Remember, we can also write this as minus the log to the base of 2. X is equals to y. So that's the same thing. If you are to sketch that, then you know that you are interchanging x and y. So you reflect the graph about the line y is equals to x. You are going to get, now if you check this one, it started on the negative x axis, which means that the new one will start on the negative y axis. It start on the negative x, cut the y, and then move up. So this one would start on the negative y, cut the x, and then move up. So that would be the inverse of that. Now this one, if you want the inverse, obviously this started on the positive x, and then it cuts the y and then move up. So we're going to have that the new one is going to start on the positive y, cut the x, and then move up. So that is the function that we are going to obtain there. So these are the inverses of logs. Now, with the parabolic functions, if you look at y is equals to x squared, if you draw this graph here, this is what we're going to get. This is generally what we're going to get. Now, if you are to interchange x and y, then you're going to get that now your graph started at 0 and it faces up to the positive y. So now the new one will also start at 0 and now will face up to the positive x. Now, if you check this graph here, if you draw a vertical line, it touches the graph on one point. So we say that it is a function, because if you can draw a vertical line from left to right, which is parallel to the y-axis, it will touch the graph on only one point. But if you are to draw a vertical line here, it touches the graph on two different points. So this is not a function. This inverse, the inverse of this parabola, is not a function. So in order for us to make it a function, we can apply what we call restriction. We can restrict the domain. If you restrict the domain, it means you can take one arm from this graph. If you can take one arm from the original graph, then it means you'll be taking one arm also on the inverse. So that is going to be a function, right? Moving on, exponents and logarithms. We are looking at the inverses. Now we are given the function f of x is 3 to the exponent of x. Determine the equation in the form of, we want the equation of the inverse. Now what are we going to do? First things first here, what we're going to do is we're going to have this written as y is equals to 3 to the exponent of x. We interchange. For us to get to the inverse, we interchange x and y. So where we see x, we put y, and where we see y, we put x. Now, if we convert this to log form, the log of a number base is equals to the exponent. So the exponent is y, so y is equals to the log of x to the base of 3. So that is how you determine that inverse. Now, sketch the graph of f as well as its inverse on the same set of axes. Now, if we can try to sketch that here, let's check f. If you check f, it's 3 to the x, which means that this graph would start on the negative x-axis, and its y-intercept is 0 and 1. So it cuts the y-axis at 0 and 1. And then that's how we draw this graph of f. Now, if we want to draw the inverse on the same set of axes, obviously this one started on the negative x-axis. If you interchange, this one would start on the negative y-axis. This one went on to cut the y-axis at 0 and 1. So this one should be cutting the y-axis at 1 and 0. So it starts here, cuts the y-axis there, and then moves this way. So these are the two graphs. The line of symmetry here is line y is equals to x. Now this would be the inverse. Now they say write down the domain of the inverse. Write down the domain of the inverse. If you check now our inverse, what would be the domain? The domain of the inverse should be the same as the range of the function, because the range was y is greater than 0. The domain should be the same as the range, you just interchange. But now if you look at this graph, you can see it's defined. This graph is defined just above the x-axis is defined just, or rather just above here, the y-axis, on it's defined on the right hand side of the y-axis. So the right hand side of the y-axis represented as the values of x. Remember, domain is the values of x, so our c here would be x should be greater than 0. That would be our domain. The graph is defined for all values of x that are on the right hand side. Right, moving on. For which values of x would be will the inverse be less than 1? Now, if we go back to the graphs, quickly. This is what we have here. If we go back to the graphs quickly here, they want where the inverse is less than 1. This is 1 is to 0. This is 0 and 1. This is 1 and 0. Now they want us to work it out where the inverse is less than 1. Now what we basically going to do here, the y value of the inverse, we don't know where the y value of the inverse is. We only know that here y should be less than 1. So we're going to find our critical values. In this case, we're going to say, where is y equals to 1? Where is f of inverse equals to 1? Because they are saying here, they are saying f of inverse of x is less than 1. We want to find it where it's equals to 1. So what we basically going to do here, we plug in the inverse equation. We got log the inverse here. Let me check. Log to the base of 3 for the number x. So this is log to the base of 3 for the number x. We want to know when it's equals to 1. So what we get here, we get that x would be equals to 3. X would be equals to 3. So we want the value of x. So we get that when x is equals to 3, y is equals to 1. So when x is equals to 3 here, y is equals to 1. So that's what we get here. So we get a point where x is 3, y is 1. So now we have our critical value. We know that x is equals to 3. So we want to know where will the function, where will the y values be less than 1. So now if you check here, this is the line that we're going to be interested in. If you move on from here, you move on to the right hand side, you can see the values of y are increasing. But if you move on to the left hand side here, you can see that the values of y are decreasing. So we want to know where the values of y are decreasing. So we are interested in this portion of the graph. So where is that portion defined? The portion here is defined between where x is between 3 as well as 0. That is where the function here is less than 1. Now, the last question on this, for which values of x will f of x times the inverse of f be negative? Now, let us redraw that again. This is what we have here, and this is what we have here. Right. Now, we are interested in the values of x where we are interested in where f of x times the inverse is less than or equals to 0. We are looking at the combination. Now, we are multiplying the two functions. We want to know where f of x times f of inverse of x is less than 0. We're going to start, the reference would be when they are both equals to 0, and this represents their x-intercept. So we're going to trace the x-intercept of f as well as the x-intercept of the inverse. If you check f, it doesn't have the x-intercept. The inverse has the x-intercept here at 1 and 0. So that's what we're going to use as our reference to try and understand this. Now, let us check our functions here. Where is the function of f above the x-axis? You can see that it's always above the x-axis here. That is the function of f. What about g? G, or rather the inverse, is below here, below the x-axis, and then here it's above the x-axis. So I was tracing it where it was below the x-axis and trace it where it was above the x-axis. Now, if we look at the question, it wants us to work out where the two graphs combined are negative. So we are looking at different signs. Either positive and negative will always give us a negative, or negative times positive will always give us a negative. So we are looking at where the graphs will have different signs. Now, if you check here, on the left hand side, it's only one graph. If you check between 0 and 1, you can see that this graph here is positive between 0 and 1, and this graph here is negative. So that's where the solution set would lie. If you look at the values above 1, or values that are greater than 1, you can see that this graph here is positive and this graph here is positive as well. That's not what we want. We want where one is positive and the other is negative. So that would be between 0, which we cannot include because it's the asymptote of the graph of the inverse. So this 3, or rather 1 here, would be included. So that is what we are basically going to get. Right, that is the inverse of exponents and logs. We're supposed to also do the inverses of a parabola, but because of time, I'm going to skip this one. And look at now differential calculus. Right, let us now look at the revision of concepts on calculus. Quickly go through that. First, we need to understand the average gradient between 2 points. That is where you have 2 points. If you have 2 points here, then you're going to use the average gradient as m is y2 minus y1 over x2 minus x1. That is the average gradient. In functional notation, it would be f of x2 minus f of x1 over x2 minus x1. That would be the average gradient. And then the gradient of a tangent to a point, we can get that through first principles, and then the x value of that particular point. We need to differentiate using the rules of differentiation, very important. And then we need to find the equation of a tangent using the concept of a derivative. Remember, always when we find the derivative, we are saying we are calculating the gradient function. Every time you find the derivative, irrespective of that function, you are working out the gradient function. Right, it tells you whatever that you're going to get will tell you how the gradient changes as the values of x changes. It has nothing to do with the function. It's not telling you how the function changes as x changes. Once you differentiate and work out the derivative, you will now be finding the values of, or rather you will now be finding the relationship between the gradient as well as the values of x. It tells you how the gradient changes as the x values changes. Right, now apply the factor and remainder theorem for third-degree functions or third-degree polynomials. That is what we use to find the x-intercept of a cubic function. We sketch and interpret a cubic function, and then we do optimization problems, that is applications of calculus. Right, now we move on to the first part here, which we deal with now is first principles as well as average gradients. Now, the mistakes that you normally make here, you have a lot of notational errors. Please note, if you check here, it's written as a function of x, f of x, and this is incorrect. This is incorrect because this should be f dash of x in order for you to find the first derivative of this. Now, if you check this one now, there's an equal sign there, which is totally wrong. We have two equal signs now. This is completely incorrect. The equal sign should only be this one. Sometimes you make this, you see the limit is written as part of the fraction. That is also not correct. Now, you forget to put brackets when doing the substitution. Sometimes for the second part, f of x, you have to put it in brackets. Sometimes you forget to do that and you remove brackets incorrectly. That is what you need to guide against. And to use the word derive as compared to differentiate. To derive an equation would be taking an equation and or rather forming a new equation from some other equation. But now to differentiate, that is now finding the derivative of that function by using the laws of differentiation or the rules of differentiation. Now if you look at example 6, determine the average gradient. I'm not going to do that. And then determine this from first principles, that I'm going to do. Remember, with average gradient, you need to find between x is equals to 2 and x is equals to 8. What we basically do is we substitute f of 2. We substitute 2 where we see x, and then we substitute 8 where we see x. So this is 2 into 8 squared plus 4. Then you're going to get f of 2 and f of 8. So you're going to know when x is 2, you're going to know what y is. When x is 8, you're going to know what y is. And then from there, you apply the gradient formula to find the average gradient. And then first principles, this I'm going to do. Now, average gradient, I'm not going to do that one because of time. I'm doing now the first principles. Now, determine f dash x from first principles. Now, remember, the first thing that we do here, we define f of x as 2x squared plus 4. Now, if we want to define another function that would be useful there, it's a function f of x plus h. F of x plus h. So what we do is we're going to substitute where we see x in the original function here, we're going to put x plus h. So this is 2 into x plus h squared plus 4. If we simplify this, this is 2 into x squared plus 2hx plus h squared plus 4. So this is 2x squared plus 4hx plus 2h squared plus 4. This is f of x plus h. Now, if we want to find the derivative, then we use first principles. F dash x would be the limit as h tends to 0 of f of x plus h minus f of x over h. Remember, this formula is in your formula sheet. You should go to your formula sheet and copy the formula exactly as it is. So we substitute now. We have the limit as h tends to 0. We know our f of x plus h. We've already worked it out here. This would be 2x squared plus 4hx plus 2h squared plus 4. And then minus our f of x. We put it in brackets. This is 2x squared plus 4. That is the original function. Divide everything by h. So this would be the limit as h tends to 0. If we open up the bracket, we get 2x squared plus 4hx plus 2h squared plus 4. And then we distribute the negative to open the bracket. This would be minus 2x squared minus 4 over h. Now if we simplify this, this would be the limit as h tends to 0 of, you see 2x squared and 2x squared are going to subtract out. Positive 4 and negative 4 are going to subtract out. So we're going to have the limit as h tends to 0 of, remember this is f prime of x, it's not f of x. So this would be 4hx plus 2h squared over h. Now if I decide to continue with it here, I can factor out h. So f dash x would be the limit as h tends to 0. If I factor out h, I'm going to get h into 4x plus 2h. This is over h. Now the h and h would divide out. I will have that this is the limit as h tends to 0 of what? 4x plus 2h. Now h tends to 0, I'll get 4x plus 2 into 0. This is given by what? 4x. H would always only tend to 0 when you no longer have the fractions, when you no longer have h as the denominator. So the goal is to make sure that h divides out somewhere so that h is no longer the denominator, because when you divide, if you substitute 0 on the denominator there, you have that the function would be undefined. So this would be, sorry, my f dash of x. So that is how we do this using first principles. Remember, this will always be in your exam paper, so you need to know how to do it, right? And the next question says, hence determine the gradient of the tangent when x is equals to minus 3. Remember, f prime of x, we need to understand this. F prime of x, this is the gradient function. That's very, very important. It's the gradient function. We've differentiated, we get what we call the gradient function. It tells us how the gradient changes as x changes. So in this case, we are given calculate the gradient of a tangent when x is minus 3. Obviously, f dash x is the gradient. So this would be 4 into minus 3. We want to know what the gradient would be if x is minus 3. So this would be given by minus 12. It would be given by minus 12. So that is how we find our gradient function. Right. I have an activity for you to do here. I need you to do this quickly. I'll just give you 3 minutes for you to work quickly through this. It's a problem on the first principles. I want you to find the derivative using first principles. Remember, only 3 minutes. Only 3 minutes. Right, your time starts now. Right, welcome back. I hope you enjoyed solving that problem. Remember, we have our WhatsApp interactive number that you can uh, uh, write your questions or where you can interact with us. That number is 0647488913. I hope you see it at the bottom of your screen there. Please send in those questions so that you can be assisted. Right. We are given the equation here. We want to determine the derivative. Right. Now the solution to that, you see that I've flagged the solution here. If you check, the first things first, you need to find f of x plus h, f of x plus h, and our f of x plus h in this case gives us the whole of this thing. And then we subtract f of x obviously from here, then you can be able to get to the answer, which is minus 6x. Now if you check how they mark substitution into the formula, substituting f of x plus h as well as f of x in that equation, and then simplifying here and then taking out h as a common factor as well as the answer. So you get that this is minus 6x as the solution set for that. Right. We are moving on to the rules of differentiation. Here we are seeing a lot of errors, notation. In terms of notation, you make a lot of notational errors. There's incorrect use of exponential laws, and then leaving out differentiation notation before the derivative is obtained, treating alpha the same way as you treat a variable. You sometimes differentiate a variable which is not included in the notation. You incorrectly convert from exponential form to set form. Remember, when you differentiate here, you need to make sure that there are no brackets. Brackets are completely removed. There are no brackets. There are no exponents in the denominators. All the variables should be numerators. All variables, there should not be any variable that is on the denominator. You should move it up there. That is very, very important. Right. Now, one other thing that you do is when you differentiate, you sometimes differentiate functions or expressions one by one. That's not what you should do. You should prepare the particular expression for differentiation. Once you differentiate each and every one of them. So if one of the elements that are there are not ready to be differentiated, then you don't differentiate up until everything is ready, then you differentiate that. Now determine f prime of x if f of x is given by that. Now what I can do here is, because I have brackets, the first thing that I should do is I should remove brackets. So this is square root of x plus 1 over square root of x. I have this twice, square root of x plus 1 over square root of x. So if I multiply that, square root of x times square root of x, I get x. If I multiply here, I get 1. If I multiply here, I get 1. If I multiply here, I get 1 over x. So this would be x plus 2 plus 1 over x. Now if you check, this is ready for differentiation, this is ready for differentiation, but this one is not ready because the variable that I should differentiate is on the denominator. I should prepare it first. So I'm going to rewrite these ones. I'm not going to differentiate these two because they are ready. I'm going to make sure that the third one is also ready. Using the inverse law here, I get that this is x to the minus 1. So all of them are now ready. I can then differentiate. Then once I differentiate, I change this notation here. I write f prime of x to show that I'm differentiating. So this would be 1 plus 0 minus, this is 1 x to the minus 2. So this would be 1 minus x to the minus 2. This would be 1 minus 1 over x squared. That is if I want to write everything as positive exponents. Right. Now, another example, we want to find the t of this. So now this is a different notation. You don't drop the t here up until you differentiate. The only time you drop this differential operator is when you've differentiated everything. Now if you check, the first one is ready for differentiation, the second one is not ready, as well as the third one. So the key here would be to make sure that all of them are ready. So I'll leave the first one because it's ready, 3 over 4 t squared plus 2 over 3. Now because the t is to the exponent of 1, if I move it up, I will get t to the minus 1. Now minus 9 over, if I convert this to exponential form, obviously if I have m, the square root of a to the n, this is equals to a n over m. The degree of the radical becomes the denominator there. Now this would be t exponent 2 over 3. So now if you check here, first one is ready, second one is ready, the third one is not ready. So we are going to continue with the operator, and I'm not going to differentiate anything until all of them are ready. So this is 3 over 4 t squared plus 2 over 3 t to the minus 1 minus 9 t, this is 9t to the minus 2 over 3. Now there are no brackets. All the variables I'm differentiating are on the numerator. I can now differentiate. Now because I'm differentiating, I'm dropping the operator d. So if I differentiate this one, I get 3 over 4 or 3 over 4. 3 over 4 here times 2. If I multiply that by 2, I get 3 over 2 t. And then minus 2 over 3 t to the minus 2 minus, I multiply 9 with 2 over 3. If I do that, I get minus, or it would be plus 6 t minus 2 over 3 minus 1. So it's minus 5 over 3. Now I can just finish this up by writing it with positive exponent. So this is minus 2 over 3 t squared plus 6 over t exponent 5 over 3. So that is what I will have for 7b. Right, example 7c, quickly work this one out. If you check here, they want dy dx and y is not the subject. So the first thing that I'll do, I'll make y the subject of the equation. So I'll have xy minus x cubed is equals to x squared. I can transpose x cubed. I'll get, this is x cubed plus x squared. Then if I divide both sides by x to make y the subject, I'll have y is equals to x squared plus x. So dy over dx would be 2x plus 1. So that is how I differentiate that one. Now I have an activity, but because of time, you guys are not going to have time to do this. I move on. Right, the equation of a tangent. We want to work out the equation of a tangent using the derivative. Now, how do we work out the equation of a tangent using the derivative? The most errors that we see, you usually confuse gradient of a tangent and x value when substituting into the equation. There is something called f of 2 and f prime of 2. These are two totally different things. F of 2 gives me the y value when x is equals to 2. F prime of 2 gives me the gradient when x is equals to 2. Please be very, very careful. Right, determine the equation of a tangent to this line. So now, if you check, we are given f of x is equals to x squared minus 6x plus 5. Now, at x is equals to 2. this x is equals to 2. Remember, when you want the equation, you will be using y is equals to, or y minus y1 is equals to m of x minus x1. So you need a gradient and a point. How do you work with this? You'll need a point x1, y1. So do we have a point in the question? Of course not. We don't have a point. But we have that x is equals to 2. So we can find the point of contact by substituting 2 where we see the function formula. So f of 2 in this case would give me the value of y when x is equals to 2. So I will have that this is 2 squared minus 6 into 2 plus 5. So this becomes 4 minus 12 plus 5. So if I have this as 4 minus 12 plus 5, this is equals to minus 3. So the point of contact when x is 2, y is minus 3. That is the point of contact, 4 minus 12 plus 5. So when x is 2, y is minus 3. That is the point of contact. That is where the function and the tangent intersect, or the point of contact between the two. Now, we want the gradient. Remember, to find the gradient, we find the derivative. So the derivative gives us the gradient. So if I can find f dash of x, or f prime of x, this is 2x minus 6. This is a new function which tells you how the gradient changes as x changes. So it gives you the relationship between gradient and the values of x. It has nothing to do with y. It's not giving you the value of y when x changes. It gives you the value of the gradient when x changes. So if I put f dash of 2, I'm going to get the gradient specifically when x is equals to 2. So this is 2 into 2 minus 6. So this is 4 minus 6. Quickly I get f prime of 2 is minus 2. It's minus 2. It's minus 2, which means that the gradient is minus 2. The gradient is minus 2. So to find the equation, I use y minus y1 is equals to m to x minus x1. Already I have a point, the point of contact, which is x1, y1. So y minus y1, 3, is the gradient, minus 2, x minus x1, x1 is 2. So if I simplify this here, I'll get that y is equals to, this would be minus 2x minus 4. So minus 2x plus 4 minus 3, this would be plus 1. Because this would be plus 4, and then when I transpose the 3. So that is the equation of that particular tangent. Right, I'm moving on here. Moving on quickly. Let's look at the graph of a cubic function. Now, we know that it is defined by f of x is ax cubed plus bx squared plus cx plus d, and it will have up to 2 stationary points. Remember, it can also have 1, and it can also have no stationary point. So it has 2, 1, or no stationary point. You should be able to draw those using the shape. A is positive. Obviously, if A is positive, then it starts by increasing, then decreases, then increases again. Right. Now, but if A is negative, it starts by decreasing. If you put our toy car here, decreases, increases, and decreases again. That is when A is less than 0. Right. Now, the steps of drawing a cubic curve, you know, you have to find the stationary points, the turning points, by equating the gradient to 0 or the derivative to 0. You have to find the x-intercept, you have to find the y-intercept, and you have to find the point of inflection. Now, and then you join those points to draw a smooth curve. Right. Now, We move on here. We get the graph of a cubic function here. You have that this graph is drawn, and we want to find the coordinates of D, E, and F from that particular graph. So the graph is already drawn for us. If you check D, E, and F, these are x-intercepts of the graph. So we need to find the x-intercept. So D, E, and F are x-intercepts. In order for us to find the x-intercept, we put y to be 0, which means we would have x cubed minus 4x squared minus 11x plus 30 is equals to 0. Now, to solve for this, we need to use the factor theorem. We'll try out factors until we get 0, plus 1 and minus 1 until we get to 0. So we're going to use our trial and error to find the factors here. So if you look at that, if you use minus 1, get it is not a factor. If you use minus 2, it's not a factor here. If you use 2, trying out 2 now, if I use 2, I get 0. So if I substitute f of 2, I get that this is 0. So I know that it means that x minus 2 is a factor. If x minus 2 is a factor, then I can use my synthetic division. I put my factor here, 2, and then I put the coefficients of all the terms here in descending order of the variable. I have 1 minus 4 minus 11 plus 30. And then I start with 0 here. 0, 1 plus 0, that's 1. 1 times 2, I get positive 2. Minus 4 plus 2 here, I'll get minus 2. I take that minus 2 and multiply that by 2 at the top. I get minus 4. 11 minus 11 minus 4, I get minus 15. Minus 15 plus or times 2 at the top there, I get minus 30, and then this would give you 0. Always the last term should give you 0. So this would now simplify to x minus 2 into x squared minus 2x minus 15 equals to 0. So this is x minus 2 into x is equals to 0. It's 15. I can use 5 and 3. Bigger number is negative. Then I have that x is equals to 2, or x is equals to minus 3, or x is equals to 5. Now at D, x is negative, so this is x at D. At F, this is at F, and then x is equals to 2, this is at E. So that's how you get these values here. Right, moving on, the graph of this, and then they say determine the coordinates of A and B. We see that A and B are the turning points. How do we determine the coordinates of the turning points? We need to differentiate. So we're going to work out f prime of x is equals to 0. What is our f prime of x? That is 3x squared minus 12x minus 11 is equals to 0. So that's what we get. So this is 3x, x is equals to 0. Obviously, we'll be using 11 and 1. Be using 11 and 1 in this case. So this should be minus 8x because we differentiate 4x here. So we're going to get that this should be negative and this should be positive. So x is 11 over 3, or x is equals to minus 1. Now when you substitute that, you're going to get f of 11 over 3. This is going to give you minus 400 over 27, and f of minus 1 is going to give you 36. So these would be your coordinates of the turning point. You differentiate, work out the x values, substitute them back to the original equation, and then you find the y values that correspond to that. Now, if you want the point of inflection, then we need to differentiate twice. So if we have f of x is equals to x cubed minus 4x squared minus 11x plus 30, we differentiate that for the first time, we get that this is 3x squared minus 8x minus 11. If you differentiate it for the second time, we get that this is 6x minus 8. We equate that to 0. So we have that 6x is equals to 8 and x is equals to 8 over 6. We get 4 over 3. That would be our point of inflection. Right. And then explain how the graph can be shifted to have two equal roots. If our graph has two equal roots, what it means is that this graph can have a turning point here, and then this is the first root, this is the second root. And then these are our equal roots if it forms the tangent with the x-axis. It can also happen on this side when we have this part here, also here, it has two equal roots. So basically, we need to move B up to there, or we move A down to there. How do we do that? We're going to say that what we basically do, we can move graph, because point A, remember, is minus 1 and 36. So we can move the graph 36 units down. That is at A. Or we can also move the graph, the turning points on B are 11 over 3 and minus 400 over 27. Can move the graph 400 over 27 units up. That's basically what you have there. Right. Because of time, I'm not going to do the rest of the questions. Time is not on our side. We're left with the derivative function. We're also left with some optimization problems. So our time is up. Time is our enemy in this case. But I'll encourage you tonight to practice. Make sure that you set those targets. Make sure that you check whether you are reaching those targets. And make sure you practice each and every topic and use the 10 minutes reading time to strategize on which questions you are going to approach and which questions you're going to start answering when the time to answer questions starts. Right. Thank you very much for tuning in. Please remember that also tomorrow we're going to have a paper 2 revision session from 2 up until 4. Sorry. Please make sure that you tune in also tomorrow to prepare for paper 2. Thank you very much for watching. Take care of each other and practice mathematics. Goodbye.